Hi class, in this lecture I want to talk about projections for vectors. So I want to take a look at this figure 4 here. I'm going to talk mostly about this figure in this lecture, but the concepts also apply in this case when you have an obtuse angle between the two vectors. But here we're just going to show where there's an acute angle between the vectors. Alright, so figure 4 representing we have this vector PQ, which will denote as vector A, and PR, which will denote as vector B. Alright. Two vectors A and B with the same initial point P. If S is the foot, so right here, of the perpendicular from R to the line containing PQ, so this right here, this is the perpendicular, then the vector represented by PS is called the vector projection of B onto A, and it's denoted projection of B onto A. The way I like to think about it is if you were to be looking straight down like this, and maybe flash like a flashlight on it or something, this would be the shadow, all right, of the projection. That's what this is right here. Okay. The scalar projection, so think about it as the magnitude, all right, of B onto A. All right, this is also called the component of B along A, is defined to be the signed magnitude of the vector projection, okay, which is the number, the magnitude of B times cosine of theta, okay, where theta is the angle, as I said, between A and B. Okay, so we have, this is a vector right here, the projection of B onto A right here. And right here we have the magnitude of it, right? Like the scalar projection of B onto A. So we can summarize these ideas as the following. All right, the scalar projection of B onto A we write as the component of B onto A, okay, is equal to the dot product of A times B divided by the magnitude of A. So this is just going to be a number, right? Because the dot product is a scalar, and then the magnitude ends up being a scalar. Finally, the vector projection of B onto A, we write projection of B onto A. We're going to end up just using this formula. It's the dot product of A and B divided by the magnitude of vector A squared times the vector A. So notice that the vector projection is the scalar projection times the unit vector in the direction of A. That's really what you're seeing there. All right, let's just do an example here. Let's find the scalar projection and vector projection of B, which is the vector 1, 1, 2, and the vector A, which is negative 2, 3, 1. All right, so the first thing we're going to do, if you look back here, in all the formulas here, you need the magnitude of A. So the first thing I'm going to do is find the magnitude of vector A. Okay, well, just following the formula for the magnitude is just equal to the square root of 14. Well, then the next thing we're going to find is the scalar projection, which is this part right here, the component of the vector, like the magnitude of it. And that's just going to be the component of B onto A, which is a dot product of A divided by the magnitude of A. Well, we already had the magnitude of A. The dot product of A and B right here is equal to 3. So this scalar projection is 3 divided by the square root of 14. Piece of cake. Next, we're going to find the vector projection. So basically what we want to do is we want to find what is this vector right here. How would we define it? Well, the vector projection is the scalar projection times the unit vector in the direction of A. So the projection of B onto A is equal to 3 divided by the square root of 14 times A over the magnitude of A. Well, here, the magnitude of A is square root of 14. The square root of 14 times square root of 14 is 14. So it'd be 3 over 14 times the vector A. When you distribute it through, you just get the following right here. So it's just a straight application of these formulas to find both the component and projection.